Japan just exposed railgun damage on an actual warship target, and the world wasn't ready. While America abandoned the technology, Japan perfected it. Here's why the US and China are scrambling to catch up. Japan's secret weapon goes public. Japan's Acquisition Technology and Logistics Agency just broke years of silence. They've finally released images showing direct impact damage from electromagnetic railgun strikes against a real maritime target. This wasn't a controlled lab environment. This was open ocean, moving targets, and hypervelocity projectiles traveling faster than most missiles. The results shocked defense analysts worldwide because they proved something critical. Railgun technology isn't science fiction anymore. America spent billions developing railguns before walking away in 2022. China displayed a prototype in 2018, then went silent. Japan? They kept working quietly, solving problems everyone else gave up on. The Asuka test platform. Japan's Acquisition Technology and Logistics Agency held its annual Defense Technology Symposium earlier this year. That's when they dropped the bombshell, showing actual impact marks on a target ship struck multiple times by prototype railgun projectiles. The test platform was JS Asuka, a 6,200-ton experimental vessel operated by the Japan Maritime Self-Defense Force. Asuka isn't just any ship, it's Japan's floating weapons laboratory, specifically designed for evaluating advanced naval systems. Earlier this year, leaked photos showed a massive railgun strapped to Asuka's rear flight deck. In September, ATLA released initial images of the weapon firing at sea. Those were just teasers. Now we know what actually happened during those shots. The railgun fired multiple rounds at a tug-like vessel being towed behind another ship. The target was moving during at least part of the test, giving ATLA critical data about stability, guidance, and projectile behavior against moving targets. The damage revealed the impact marks told the whole story. Cross-shaped puncture points caused by fin-stabilized dart-shaped projectiles, maintaining stable flight all the way to target. For railgun testing, that flight stability is absolutely essential. The fact that Japan achieved consistent hits represents a major technical breakthrough that eluded American engineers for years. ATLA also fired the gun at a 45-degree upward angle to gather pure ballistic data, measuring arc, drag, velocity loss, and long-range potential. They mounted sensors across Asuka's flight deck, including cameras right under the barrel for remote aiming, high-speed cameras to capture projectile exit, and small radar units to track velocity. They even had drones filming from above. This level of data collection shows Tokyo is building a comprehensive analytical dataset, exactly what you need to transform a prototype into combat-ready hardware. The engineering monster. Here's where it gets insane. Japan's prototype railgun required 4 full shipping containers of support equipment strapped onto Asuka's flight deck. Inside those containers, electrical systems, cooling units, power conditioning equipment, everything required to keep the gun operational. Unlike conventional guns, railguns are brutally hungry for power. They also generate monstrous heat and enormous stress on barrels every time a projectile launches at several thousand meters per second. This is exactly where the US Navy hit a brick wall. Not because railguns don't work, they absolutely do, but because integrating them onto real warships requires massive space, power generation, and cooling capacity that existing destroyers and cruisers simply don't have. But Japan seems determined to push ahead anyway. And to their credit, they're solving core problems one by one. Barrel life breakthrough ATLA revealed that Japan's latest tests show barrel life of more than 200 rounds at around 2,300 meters per second. That's a massive deal. Barrel wear has always been one of the most brutal engineering problems for railguns. As rails degrade, accuracy and range plummet while catastrophic failure risk rises. Just last year, Japan's reported velocity was about 2,230 meters per second. Not only did they increase performance, they nearly doubled the barrel life goal they set earlier, which was around 120 rounds. This suggests Japan has made real progress in material science, cooling technology, and electromagnetic wear reduction. These are the exact problems that killed America's railgun program. The hypervelocity projectile. What truly separates Japan's railgun projectile from everything else is the internal stabilization system known as the hypervelocity projectile. This isn't just a metal slug. This is a precisely engineered kinetic weapon designed with an almost flawless aerodynamic form. At hypersonic speeds reaching over Mach 7, even the slightest imperfection could destabilize trajectory. Japan designed the projectile with an elongated solid structure and an ultra-precise pointed tip. The tip is crafted through high-tech fabrication processes, allowing every micron of the projectile's surface to reduce air drag. The material composition remains classified, but military analysts suspect tungsten or tungsten-carbon alloy as the primary component. Tungsten has an exceptionally high melting point near 3,400 degrees Celsius, meaning the projectile doesn't melt while traveling at hypersonic speed through Earth's atmosphere. Additionally, its high density provides penetration capabilities far superior to conventional rounds. In various tests, the projectile pierced thick steel plates without needing explosives. All destructive power comes purely from immense kinetic energy, stability under extreme forces. Here's where Japan's engineering gets truly impressive. The projectile must withstand extreme acceleration forces when the railgun fires. Japan's electromagnetic railgun generates enormous energy, triggering sudden accelerations equivalent to thousands of G-forces. Conventional projectiles would be destroyed instantly, but Japan's electromagnetic rounds are produced using advanced metallurgical engineering that prevents internal fractures or distortions. Engineers must balance material strength with overall projectile weight. Too heavy, and the railgun requires excessive energy. Too light, and it loses stability and accuracy. Japan found the sweet spot. Why Japan is doing this? A practical railgun offers a warship flexible, long-range, high-velocity weapons that can hit targets in the air, at sea, or on land. It has potential to defend against hypersonic missiles, one of Japan's biggest concerns given evolving missile arsenals in the region from China and North Korea. And because the rounds are small, solid metal projectiles, essentially inert slugs, you can carry a massive magazine for a fraction of the cost of traditional missiles. If you're at sea for long durations and can't reload expensive missiles, the ability to fire dozens or even hundreds of high-velocity projectiles is a game-changer. The cost advantage. The projectile also offers significant strategic advantages in terms of cost. Unlike interceptor missiles that cost millions per unit, railgun rounds are relatively inexpensive because they lack complex guidance systems or propellants. Japan understands that in future warfare, volume of fire will matter immensely. With low-cost electromagnetic rounds, Japan could fire dozens or even hundreds of shots during sustained defense operations, an enormous advantage in long-term maritime engagements traditionally dominated by expensive missile systems. America's failed program. The U.S. Navy was the global leader starting in 2005, pouring years of testing into railgun prototypes. They planned to move testing to sea but never made it. The challenges, power demands, barrel life, cooling, and integration piled up. By 2022, the program was publicly shelved. Japan, meanwhile, kept going. And they're not alone. France and Germany are jointly developing railgun tech. Turkey has been very vocal about its progress. And China, at least for a time, displayed a railgun prototype mounted on a large turret aboard a PLN vessel back in 2018. The status of that program remains unclear, but the interest is global. International collaboration. Here's the part people might not expect. ATLA has reportedly met with the U.S. Navy to discuss America's past railgun work and how Japan might leverage that knowledge. There's also talk of future collaboration. On top of that, Japan has already signed a cooperation agreement with the Franco-German Research Institute ISL, specifically for developing railgun technologies. Put it all together, and you see the real story. Railguns aren't dead, not even close. They're evolving, and Japan is positioning itself at the front of the pack. The future of naval warfare. The newly released data makes one thing clear. Railgun damage to a real ship wasn't just a successful experiment, it was a milestone. Japan is gathering real-world, at-sea performance data that the U.S. Navy never obtained. And while it will still take years to develop an operational railgun that can survive the brutal demands of naval warfare, Japan has officially crossed the line from laboratory curiosity to credible working prototype. Roadmap expansion. It doesn't stop at the Navy. ATLA's roadmap now includes both naval and land-based railgun systems, including truck-mounted versions. Japan sees railguns as part of a broader defensive ecosystem, especially against high-speed, high-altitude threats. This multi-platform approach means Japan is thinking strategically about how electromagnetic weapons fit into their entire defense architecture. Japan just proved what America couldn't, that railguns are ready for prime time. While the US walked away and China went silent, Japan solved the impossible problems and turned science fiction into battlefield reality. The damage revealed on that target ship isn't just impressive, it's a warning shot to every Navy on Earth. Which country surprised you most? Drop your thoughts below and subscribe for more defense technology breakthroughs.